Technetium. Technetium is a chemical element with symbol Tc and atomic number 43. It is the lightest element whose isotopes are all radioactive, none are stable, excluding the fully ionized state of 97 Tc. Nearly all technetium is produced synthetically, and only about 18,000 tons can be found at any given time in the Earth's crust. Naturally occurring technetium is a spontaneous fission product in uranium ore and thorium ore, the most common source, or the product of neutron capture in molybdenum ores. This silvery gray, crystalline transition metal lies between rhenium and manganese in group 7 of the periodic table, and its chemical properties are intermediate between those of these two adjacent elements. The most common naturally occurring isotope is 99 Tc. Many of technetium's properties were predicted by Dmitry Mendeleev before the element was discovered. Mendeleev noted a gap in his periodic table and gave the undiscovered element the provisional name manganese. In 1937, technetium became the first predominantly artificial element to be produced, hence its name. One short-lived gamma-ray-emitting nuclear isomer of technetium, technetium-99m, is used in nuclear medicine for a wide variety of diagnostic tests, such as bone cancer diagnoses. The ground state of this nuclide, technetium-99, is used as a gamma-ray-free source of beta particles. Long-lived technetium isotopes produced commercially are byproducts of the fission of uranium-235 in nuclear reactors and are extracted from nuclear fuel rods. Because no isotope of technetium has a half-life longer than 4.2 million years, the 1952 detection of technetium in red giants helped to prove that stars can produce heavier elements. From the 1860s through 1871, early forms of the periodic table proposed by Dmitry Mendeleev contained a gap between molybdenum and ruthenium. In 1871, Mendeleev predicted this missing element would occupy the empty place below manganese and have similar chemical properties. Mendeleev gave it the provisional name manganese because the predicted element was one place down from the known element manganese. Many early researchers, both before and after the periodic table was published, were eager to be the first to discover and name the missing element. Its location in the table suggested that it should be easier to find than other undiscovered elements. German chemists Walter Noddack, Otto Berg, and Ida Tack reported the discovery of element 75 and element 43 in 1925, and named element 43 mausoleum. The group bombarded columbite with a beam of electrons and deduced element 43 was present by examining X-ray diffraction spectrograms. The wavelength of the X-rays produced is related to the atomic number by a formula derived by Henry Moseley in 1913. The team claimed to detect a faint X-ray signal at a wavelength produced by element 43. Later experimenters could not replicate the discovery, and it was dismissed as an error for many years. Still, in 1933, a series of articles on the discovery of elements quoted the name mausoleum for element 43. Whether the 1925 team actually did discover element 43 is still debated. The discovery of element 43 was finally confirmed in a 1937 experiment at the University of Palermo in Sicily by Carlo Perrier and Emilio Segre. In mid-1936, Segre visited the United States, first Columbia University in New York and then the Lawrence Berkeley National Laboratory in California. He persuaded cyclotron inventor Ernest Lawrence to let him take back some discarded cyclotron parts that had become radioactive. Lawrence mailed him a molybdenum foil that had been part of the deflector in the cyclotron. Segre enlisted his colleague Perrier to attempt to prove, through comparative chemistry, that the molybdenum activity was indeed from an element with the atomic number 43. In 1937 they succeeded in isolating the isotopes technetium-95m and technetium-97. University of Palermo officials wanted them to name their discovery panormium, after the Latin name for Palermo, Panormus. In 1947 element 43 was named after the Greek word tau epsilon chi nu eta tau, meaning artificial, since it was the first element to be artificially produced. Segre returned to Berkeley and met Glenn T. Seaborg. They isolated the metastable isotope technetium-99m, which is now used in some 10 million medical diagnostic procedures annually. In 1952, astronomer Paul W. Merrill in California detected the spectral signature of technetium in light from S-type red giants. The stars were near the end of their lives, yet were rich in this short-lived element, indicating that it was being produced in the stars by nuclear reactions. This evidence bolstered the hypothesis that heavier elements are the product of nucleosynthesis in stars. More recently, such observations provided evidence that elements are formed by neutron capture in the S process. Since that discovery, there have been many searches in terrestrial materials for natural sources of technetium. In 1962, technetium-99 was isolated and identified in pitchblende from the Belgian Congo in extremely small quantities. There it originates as a spontaneous fission product of uranium-238. The Oklo Natural Nuclear Fission Reactor contains evidence that significant amounts of technetium-99 were produced and have since decayed into ruthenium-99. Technetium is a silvery gray radioactive metal with an appearance similar to platinum, commonly obtained as a gray powder. The crystal structure of the pure metal is hexagonal close-packed. Atomic technetium has characteristic emission lines at these wavelengths of light, 363.3 nm, 403.1 nm, 426.2 nm, 429.7 nm, and 485.3 nm. The metal form is slightly paramagnetic, meaning its magnetic dipoles align with external magnetic fields, but will assume random orientations once the field is removed. Pure, metallic, single-crystal technetium becomes a type II superconductor at temperatures below 7.46 K. Below this temperature, technetium has a very high magnetic penetration depth, greater than any other element except niobium. Technetium is located in the 7th group of the periodic table, between rhenium and manganese. As predicted by the periodic law, its chemical properties are between those two elements. Of the two, technetium more closely resembles rhenium, particularly in its chemical inertness and tendency to form covalent bonds. Unlike manganese, technetium does not readily form cations. Technetium exhibits 9 oxidation states from 1 to +7, with +4, +5, and +7 being the most common. Technetium dissolves in aqua regia, nitric acid, and concentrated sulfuric acid, but it is not soluble in hydrochloric acid of any concentration. Metallic technetium slowly tarnishes in moist air and, in powder form, burns in oxygen. Technetium can catalyze the destruction of hydrazine by nitric acid, and this property is due to its multiplicity of valencies. This caused a problem in the separation of plutonium from uranium in nuclear fuel processing, where hydrazine is used as a protective reductant to keep plutonium in the trivalent rather than the more stable tetravalent state. The problem was exacerbated by the mutually enhanced solvent extraction of technetium and zirconium at the previous stage, and required a process modification. The most prevalent form of technetium that is easily accessible is sodium pertechnetate, Na. The majority of this material is produced by radioactive decay from 2-pertechnetate. TCO4 behaves analogously to perchlorate, both of which are tetrahedral. Unlike permanganate, it is only a weak oxidizing agent. Related to pertechnetate is heptoxide. This pale yellow, volatile solid is produced by oxidation of Tc metal and related precursors. It is a very rare example of a molecular metal oxide, other examples being OSO4 and RuO4. It adopts a centrosymmetric structure with two types of TCO bonds with 167 and 184 pm bond lengths. Technetium heptoxide hydrolyzes to pertechnetate and pertechnetic acid, depending on the pH. HTCO4 is a strong acid. In concentrated sulfuric acid, converts to the octahedral form TCO3-2, the conjugate base of the hypothetical triaquo complex plus. Technetium forms a dioxide, disulfide, diselenide, and ditelluride. An ill-defined Tc2S7 forms upon treating pertechnate with hydrogen sulfide. It thermally decomposes into disulfide and elemental sulfur. Similarly, the dioxide can be produced by reduction of the Tc2O7. Unlike the case for rhenium, a trioxide has not been isolated for technetium. However, TCO3 has been identified in the gas phase using mass spectrometry. Technetium forms the simple complex TCH29. The potassium salt is isostructural with Re29. The following binary technetium halides are known: TCF6, TCF5, TCCl4, TCBr4, TCBr3, alpha TCCl3, beta TCCl3, TCI3, alpha TCCl2, and beta TCCl2. The oxidation states range from Tc to Tc. Technetium halides exhibit different structure types, such as molecular octahedral complexes, extended chains, layered sheets, and metal clusters arranged in a three-dimensional network. These compounds are produced by combining the metal and halogen or by less direct reactions. TCCl4 is obtained by chlorination of Tc metal or Tc2O7 upon heating. TCCl4 gives the corresponding Tc and Tc chlorides. The structure of TCCl4 is composed of infinite zigzag chains of edge-sharing TCCl6 octahedra. It is isomorphous to transition metal tetrachlorides of zirconium, hafnium, and platinum. Two polymorphs of technetium trichloride exist, alpha and beta TCCl3. The alpha polymorph is also denoted as Tc3Cl9. It adopts a confacial bioctahedral structure. It is prepared by treating the chloroacetate Tc24Cl2 with HCl. Like Re3Cl9, the structure of the alpha polymorph consists of triangles with short distances. Beta TCCl3 features octahedral Tc centers, which are organized in pairs, as seen also for molybdenum trichloride. TCBr3 does not adopt the structure of either trichloride phase. Instead, it has the structure of molybdenum tribromide, consisting of chains of confacial octahedra with alternating short and long Tc-Tc contacts. TCI3 has the same structure as the high-temperature phase of TiI3, featuring chains of confacial octahedra with equal Tc-Tc contacts. Several anionic technetium halides are known. The binary tetrahalides can be converted to the hexahalides too, which adopt octahedral molecular geometry. More reduced halides form anionic clusters with Tc-Tc bonds. The situation is similar for the related elements of MO, W, Re. These clusters have the nuclear ID Tc4, Tc6, Tc8, and Tc13. The more stable Tc6 and Tc8 clusters have prism shapes where vertical pairs of Tc atoms are connected by triple bonds and the planar atoms by single bonds. Every technetium atom makes 6 bonds, and the remaining valence electrons can be saturated by 1 axial and 2 bridging ligand halogen atoms such as chlorine or bromine. Technetium forms a variety of coordination complexes with organic ligands. Many have been well investigated because of their relevance to nuclear medicine. Technetium forms a variety of compounds with TCC bonds, i.e. organotechnetium complexes. Prominent members of this class are complexes with CO, arene, and cyclopentadienyl ligands. The binary carbonyl Tc210 is a white volatile solid. In this molecule, 2 technetium atoms are bound to each other. Each atom is surrounded by octahedra of 5 carbonyl ligands. The bond length between technetium atoms, 303 pm, is significantly larger than the distance between 2 atoms in metallic technetium. Similar carbonyls are formed by technetium's congeners, manganese and rhenium. Interest in organotechnetium compounds has also been motivated by applications in nuclear medicine. Unusual for other metal carbonyls, Tc forms equocarbonyl complexes, prominent being plus. Technetium, with atomic number 43, is the lowest numbered element in the periodic table of which all isotopes are radioactive. The second lightest exclusively radioactive element, promethium, has an atomic number of 61. Atomic nuclei with an odd number of protons are less stable than those with even numbers, even when the total number of nucleons is even, and odd-numbered elements have fewer stable isotopes. The most stable radioactive isotopes are technetium-98 with a half-life of 4.2 million years, technetium-97 with 2.6 Ma, and technetium-99 with 211,000 years. 30 other radioisotopes have been characterized with mass numbers ranging from 85 to 118. Most of these have half-lives that are less than an hour, the exceptions being technetium-93, technetium-94, technetium-95, and technetium-96. The primary decay mode for isotopes lighter than technetium-98 is electron capture, producing molybdenum. For technetium-98 and heavier isotopes, the primary mode is beta emission, producing ruthenium, with the exception that technetium-100 can decay both by beta emission and electron capture. Technetium also has numerous nuclear isomers, which are isotopes with one or more excited nucleons. Technetium-97m is the most stable, with a half-life of 91 days. This is followed by technetium-95m, and technetium-99m. Technetium-99m emits only gamma rays and decays to technetium-99. Technetium-99 is a major product of the fission of uranium-235, making it the most common and most readily available isotope of technetium. 1 gram of technetium-99 produces 6.2 times 108 disintegrations a second. Technetium occurs naturally in the Earth's crust in minute concentrations of about 0.003 parts per trillion. This totals about 18,000 tons at any given time, assuming the mass of the Earth's crust is 60,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,000,6 times 1021 kilograms. Technetium is so rare because technetium-98's half-life is only 4.2 million years. More than 1,000 of such periods have passed since the formation of the Earth, so the probability for the survival of even one atom of primordial technetium is effectively zero. However, small amounts exist as spontaneous fission products in uranium ores. A kilogram of uranium contains an estimated 1 nanogram of technetium. Some red giant stars with the spectral types S, M, and N contain a spectral absorption line indicating the presence of technetium. These red giants are known informally as technetium stars. In contrast to the rare natural occurrence, bulk quantities of technetium-99 are produced each year from spent nuclear fuel rods, which contain various fission products. The fission of a gram of uranium-235 in nuclear reactors yields 27 mg of technetium-99, giving technetium a fission product yield of 6.1%. Other fissile isotopes produce similar yields of technetium, such as 4.9% from uranium-233 and 6.21% from plutonium-239. An estimated 49,000 TBq of technetium was produced in nuclear reactors between 1983 and 1994, by far the dominant source of terrestrial technetium. Only a fraction of the production is used commercially. Technetium-99 is produced by the nuclear fission of both uranium-235 and plutonium-239. It is therefore present in radioactive waste and in the nuclear fallout of fission bomb explosions. Its decay, measured in becquerels per amount of spent fuel, is the dominant contributor to nuclear waste radioactivity after about 104 to 106 years after the creation of the nuclear waste. From 1945 to 1994, an estimated 160 TBq of technetium-99 was released into the environment during atmospheric nuclear tests. The amount of technetium-99 from nuclear reactors released into the environment up to 1986 is on the order of 1000 TBq, primarily by nuclear fuel reprocessing. Most of this was discharged into the sea. Reprocessing methods have reduced emissions since then, but as of 2005 the primary release of technetium-99 into the environment is by the Sellafield plant, which released an estimated 550 TBq from 1995-1999 into the Irish Sea. From 2000 onwards the amount has been limited by regulation to 90 TBq per year. Discharge of technetium into the sea resulted in contamination of some seafood with minuscule quantities of this element. For example, European lobster and fish from West Cumbria contain about 1 Bq/kg of technetium. The metastable isotope technetium-99m is continuously produced as a fission product from the fission of uranium or plutonium in nuclear reactors. Because used fuel is allowed to stand for several years before reprocessing, all molybdenum-99 and technetium-99m is decayed by the time that the fission products are separated from the major actinides in conventional nuclear reprocessing. The liquid left after plutonium-uranium extraction contains a high concentration of technetium as TCO4, but almost all of this is technetium-99, not technetium-99m. The vast majority of the technetium-99m used in medical work is produced by irradiating dedicated highly enriched uranium targets in a reactor, extracting molybdenum-99 from the targets in reprocessing facilities, and recovering at the diagnostic center the technetium-99m produced upon decay of molybdenum-99. Molybdenum-99 in the form of molybdate Mu24 is adsorbed onto acid alumina in a shielded column chromatograph inside a technetium-99m generator. Molybdenum-99 has a half-life of 67 hours, so short-lived technetium-99m, which results from its decay, is being constantly produced. The soluble Pertechnetate TCO4 can then be chemically extracted by elution using a saline solution. A drawback of this process is that it requires targets containing uranium-235, which are subject to the security precautions of fissile materials. Almost two-thirds of the world's supply comes from two reactors, the National Research Universal Reactor at Chalk River Laboratories in Ontario, Canada, and the High Flux Reactor at Nuclear Research and Consultancy Group in Petten, Netherlands. All major reactors that produce technetium-99m were built in the 1960s and are close to the end of life. The two new Canadian multipurpose applied physics lattice experiment reactors planned and built to produce 200% of the demand of technetium-99m relieved all other producers from building their own reactors. With the cancellation of the already tested reactors in 2008, the future supply of technetium-99m became problematic. The Chalk River reactor was shut down for maintenance in August 2009, and reopened in August 2010. The Petten reactor had a 6-month scheduled maintenance shutdown on Friday, February 19, 2010, and reopened September 2010. With millions of procedures relying on technetium-99m every year, the low supply has left a gap, leaving some practitioners to revert to techniques not used for 20 years. Somewhat allaying this issue is an announcement from the Polish Maria Research Reactor that they have developed a technique to isolate technetium. The long half-life of technetium-99 and its potential to form anionic species creates a major concern for long-term disposal of radioactive waste. Many of the processes designed to remove fission products in reprocessing plants aim at cationic species such as cesium and strontium. Hence the Pertechnetate escapes through those processes. Current disposal options favor burial in continental, geologically stable rock. The primary danger with such practice is the likelihood that the waste will contact water, which could leach radioactive contamination into the environment. The anionic pertechnetate and iodide tend not to adsorb into the surfaces of minerals, and are likely to be washed away. By comparison, plutonium, uranium, and cesium tend to bind to soil particles. Technetium could be immobilized by some environments, such as microbial activity in lake bottom sediments, and the environmental chemistry of technetium is an area of active research. An alternative disposal method, transmutation, has been demonstrated at CERN for technetium-99. In this process, the technetium is bombarded with neutrons to form the short-lived technetium-100, which decays by beta decay to ruthenium-100. If recovery of usable ruthenium is a goal, an extremely pure technetium target is needed. If small traces of the minor actinides such as americium and curium are present in the target, they are likely to undergo fission and form more fission products which increase the radioactivity of the irradiated target. The formation of ruthenium-106 from the fresh fission is likely to increase the activity of the final ruthenium metal, which will then require a longer cooling time after irradiation before the ruthenium can be used. The actual separation of technetium-99 from spent nuclear fuel is a long process. During fuel reprocessing, it comes out as a component of the highly radioactive waste liquid. After sitting for several years, the radioactivity reduces to a level where extraction of the long-lived isotopes, including technetium-99, becomes feasible. A series of chemical processes yields technetium-99 metal of high purity. Molybdenum-99, which decays to form technetium-99m, can be formed by the neutron activation of molybdenum-98. When needed, other technetium isotopes are not produced in significant quantities by fission, but are manufactured by neutron irradiation of parent isotopes. The feasibility of technetium-99m production with the 22 MeV proton bombardment of a molybdenum-100 target in medical cyclotrons following the reaction 100MO99 was demonstrated in 1971. The recent shortages of medical technetium-99m reignited the interest in its production by proton bombardment of isotopically enriched molybdenum-100 targets. Other techniques are being investigated for obtaining molybdenum-99 from molybdenum-100 via or reactions in particle accelerators. Technetium-99m is used in radioactive isotope medical tests. For example, technetium-99m is a radioactive tracer that medical imaging equipment tracks in the human body. It is well suited to the role because it emits readily detectable 140 keV gamma rays, and its half-life is 6.01 hours. The chemistry of technetium allows it to be bound to a variety of biochemical compounds, each of which determines how it is metabolized and deposited in the body, and this single isotope can be used for a multitude of diagnostic tests. More than 50 common radiopharmaceuticals are based on technetium-99m for imaging and functional studies of the brain, heart muscle, thyroid, lungs, liver, gallbladder, kidneys, skeleton, blood, and tumors. The longer-lived isotope, technetium-95m with a half-life of 61 days, is used as a radioactive tracer to study the movement of technetium in the environment and in plant and animal systems. Technetium-99 decays almost entirely by beta decay, emitting beta particles with consistent low energies and no accompanying gamma rays. Moreover, its long half-life means that this emission decreases very slowly with time. It can also be extracted to a high chemical and isotopic purity from radioactive waste. For these reasons, it is a National Institute of Standards and Technology standard beta emitter, and is used for equipment calibration. Technetium-99 has also been proposed for optoelectronic devices and nanoscale nuclear batteries. Like rhenium and palladium, technetium can serve as a catalyst. In processes such as the dehydrogenation of isopropyl alcohol, it is a far more effective catalyst than either rhenium or palladium. However, its radioactivity is a major problem in safe catalytic applications. When steel is immersed in water, adding a small concentration of potassium pertechnetate to the water protects the steel from corrosion, even if the temperature is raised to 250 degrees C. For this reason, pertechnetate has been used as an anodic corrosion inhibitor for steel, although technetium's radioactivity poses problems that limit this application to self-contained systems. While Cro-2,4 can also inhibit corrosion, it requires a concentration 10 times as high. In one experiment, a specimen of carbon steel was kept in an aqueous solution of pertechnetate for 20 years and was still uncorroded. The mechanism by which pertechnetate prevents corrosion is not well understood, but seems to involve the reversible formation of a thin surface layer. One theory holds that the pertechnetate reacts with the steel surface to form a layer of technetium dioxide which prevents further corrosion. The same effect explains how iron powder can be used to remove pertechnetate from water. The effect disappears rapidly if the concentration of pertechnetate falls below the minimum concentration or if too high a concentration of other ions is added. As noted, the radioactive nature of technetium makes this corrosion protection impractical in almost all situations. Nevertheless, corrosion protection by pertechnetate ions was proposed for use in boiling water reactors. Technetium plays no natural biological role and is not normally found in the human body. Technetium is produced in quantity by nuclear fission, and spreads more readily than many radionuclides. It appears to have low chemical toxicity. For example, no significant change in blood formula, body and organ weights, and food consumption could be detected for rats which ingested up to 15 g of technetium-99 per gram of food for several weeks. The radiological toxicity of technetium is a function of compound, type of radiation for the isotope in question, and the isotope's half-life. All isotopes of technetium must be handled carefully. The most common isotope, technetium-99, is a weak beta emitter. Such radiation is stopped by the walls of laboratory glassware. The primary hazard when working with technetium is inhalation of dust. Such radioactive contamination in the lungs can pose a significant cancer risk. For most work, careful handling in a fume hood is sufficient, and a glove box is not needed.